Hi everyone, welcome to the next video in our week 1 series on box plots. A box plot, also sometimes called a box and whisker plot, is a graph that shows the center and spread of the data. To construct a box plot, we need 5 values, and lucky for us, they're 5 values we already know how to find and can find fairly quickly with a calculator. We need the minimum or smallest number in the list, first quartile, the median or second quartile, our third quartile, and our maximum. Together, these 5 numbers are often called the 5-number summary. And these 5 numbers are what we build our box plot with. You can see that all 5 of those numbers are also something we know how to calculate by hand, and the worst calculation we could possibly see is adding 2 numbers and dividing by 2. This type of graph and these types of numbers are easy to do on the fly. If you're out in the field and you're trying to get a quick sense of what your data looks like, this is something you can easily sketch on a scrap of paper without needing a whole lot of tech. So box plots have the advantage of being quick, so that if you're looking for something in the field, or you've got a lot of sample sets that you need to go through, this is something that you can move quickly through that set of samples because the calculations are fast and the box plot is also pretty fast to construct, and all of that can be done in an app or a calculator pretty quickly. Here's an example of a box plot, and you can see those 5 numbers from the 5-number summary: the min, first quartile, median, third quartile, max. You can see why it's called a box or a box and whisker plot. The box represents that interquartile range, the distance from Q1 to Q3. And then the whiskers represent the distance from those quartiles to the outer edges of the data. So I see how spread out my data is by the width of those box sections and whiskers, and I can see very clearly where one of my measures of center is. That median is the halfway point for my data. Because we're using quartiles as our measurements, and we know quartiles divide data into 4 equal chunks, 25% of the data values should be represented by that lower whisker. 25% of the data should be between the lower quartile and the median in this section of box. A quarter of the data is between the median and the third quartile. And then a 25% or quarter of the data is in that upper whisker. The smaller that chunk of graph, the more tightly packed that 25% of the data is. 50%, specifically the middle 50%, is in the boxy part, the width of which is that interquartile range. So we're going to go ahead and do a couple and then talk about some special cases really quick. So we're given a set of data, and then we're asked to construct a box plot. And you can see I've already written the 5-number summary here. To do that, I took this data and I plugged it in a calculator, and I run 1var stats on it, on a TI. Or if you're in GeoGebra, enter the list quartile 1, median quartile 3. When I did it, I got the quartiles were 2, 7, and 9. And then the smallest is 1, the biggest is 1.5. The first step for my box plot is I need a number line, and I need the number line to extend from at least the minimum to the maximum. And you can see that my graph starts a little bit below 1 and ends a little bit above 11.5. I find it nice to leave a little bit of wiggle room on the edges of those graphs, but it's not mandatory. You can put 1 on one edge and 11.5 on the other. What you do need to have is a proper scale, meaning the gaps between those tick marks or numbers on your scale need to be the same. Here you can see I counted by 1, each box is 1, and I labeled every other. So 0, 1, 2, 3, 4. So those gaps are uniform. The next step is we're going to draw lines vertically above each of the numbers in our 5-number summary. So I'm going to draw a vertical line here at 1. I'm going to draw a vertical line at 2, a vertical line at 7, which is right here, 1 at 9, and 1 at 11.5, which is halfway between 11 and 12, which is right about here. So I have those 5 markers. Now I need the box and whiskers. The whiskers connect the minimum to the first quartile and the maximum to the third quartile. And then the boxy part is Q1 to Q3. Q1 to Q3. So boxy part first for me. Here's quarter 1, go all the way to quarter 3 and then back. And then the whiskers go out from the edges of the box to the max and min. And looking at this box plot looks rather different than the sample box plot we saw on the last page. So this data has a different spread. I can see that the lower quarter of my data is squished together. There's a whole bunch of data down at 1 and 2, right? A quarter of that data is down here at 1 and 2. The next 25% of data is really spread out from 2 all the way to 7. So that next middle chunk is right here, and there's much bigger spread. The third quarter of the data, significantly less spread out than the second quarter, but a little bit more spread out than the first quarter. It extends from 7 to 9, and then the last one is from 9 to 11.5. The other thing that I can see from this data is it's not nice, pretty, and symmetric. I can't cut it in half and get 2 perfect mirror images. Part of it's squashed together, part of it's really spread out. We're going to see that as a factor later when making decisions about how to summarize our data. You can use color here, that's optional. I like to make my graphs pretty. I'd like you to try one on your own. You've been given a data set that represents the number of pages in 40 books on a shelf. And you've been asked to construct a box plot. It says using a graphing calculator, which you don't need, but you do need that graphing calculator to find your 5-number summary, and then state that interquartile range. So go ahead and pause the video really quick, grab your graphing calculator and find that 5-number summary, and then sketch a quick box plot. Okay, so when I did it on my TI-84, I got the following 5-number summary: 136, 237, 322, 395, and 512. You should definitely check me on that. And then I built a box plot based on that. So vertical lines at those 5 numbers, connect the middle 3 to form the box. And I get something that looks like this. Again, you'll notice it looks a little different than the hand-drawn one I drew before. First, I see labels that I didn't see before. Those 5 numbers from the 5-number summary are above the hash marks in the graph. So on graphs like this, where it's really difficult to take that hash mark and trace it down to what number it represents on the axis, because that axis is so wide, it represents such a big spread of numbers, it is appropriate to label those locations on your box plot. That makes it more legible and allows readers to clearly identify those 5 important numbers. The other thing you'll notice is that this graph is clearly not drawn by hand, as that is neater than I can draw. So what I did is I used GeoGebra. GeoGebra has a really nice box plot command. Words are hard. So if you'll give me just a second, what I'm doing off to the side that you can't really see right now is just like we did in the last video, I'm taking that data and I'm entering it into a list. I'm going to do it, actually let me pull it on screen and I'll show you what I'm doing. You can enter the raw data and it'll auto-calculate the 5-number summary for you, or you can enter that 5-number summary. But let's pull up the box plot function call. Let me zoom in so we can all see this. Hold on a second. Okay, so I'm going to type box plot, and you can see it automatically pops up. And what it's asking for here is it's asking for a couple of things. So it says that first row, where do I want the middle of my box plot to be? And how tall do I want my box plot to be? And then what is my raw list of data? And then the last one I think is a little bit easier to work with. It asks me where I want the center of my graph to be, how tall I want it to be, and then my 5-number summary. So let's go ahead and do that one. I'm going to shrink this back down. So I'm going to type box plot. Let's try putting it at 10, making it 5 tall, and then those 3 numbers. So 136, 237, 322, 395, and 512. And you'll notice it spits back out the median. But what we should see on the graph, if we scroll out appropriately here, we need to get all the way out to the hundreds, is, aha, we start to see the edges of our box plot. And you'll notice by the time I've zoomed in enough to see it, it looks kind of skinny, and it's got some text in the middle. So we can play with this to make it pretty. When I click on the box plot, those 3 little dots give me a settings menu, and I can turn off the label, which is always kind of nice. So that gets rid of the text. You can also change the color if you want for some reason. Lots of ways to change the color. You can make it pretty. You can make the lines thicker. You can make it more opaque or less opaque. But what I really want to do is I want to kind of shift it up and make it a little taller so I can see what is going on, because that's kind of difficult to read as it is right now. So I'm going to go back and fiddle with these 2 first numbers, which tells me where is my midpoint. So let's shift it up to 50. And then how wide is it? Let's try 25. And that looks a little bit prettier. That I can see clearly. It looks very similar to what I saw before. The hash marks are nice and clear, but you'll also notice because that range of values is so wide, I then can't read where those hash marks are. And so that's where you need to start adding text in. You can do that on GeoGebra. I did it using, I think, Photoshop. But you can just type text and then asterisk, not asterisks, apostrophes, quotation marks, one of those. That's why you teach math and not English. And type what you want to type. So we know our minimum is 136. I can type that as text. The only catch is it automatically drops the text at 0. So then you have to like pick it up and drag it where you want it. But that's not very difficult to do. So GeoGebra is a great tool to construct a box plot pretty quickly, and it gives you a lot of options to modify it so that it looks nice, change its color, give it labels, all that kind of fun stuff. Okay, 2 special cases and then we can be done. First, this is a sample box plot, and you will notice there are parts of that box plot that are missing. So in this box plot, we are missing both whiskers and a portion of the box. And that tells me that the original data set had repeated values, meaning there were a whole bunch of numbers that were the same. And so that affects what my box plot looks like. For this specific example, we're missing 2 things. So first, we're missing that lower whisker. That lower whisker has been squashed into the bottom edge of the box. So that tells me that lower 25% that would normally be a spread out whisker is all 1. The lower 25% of my data list is a repeated value, 1. The next chunk of the box is from 1 to 5. That next chunk of the box is nice and spread out. But then you'll notice there's no second part of the box up here. And what that tells me is the third 25% of the data, that second part of the box, has all been squashed down to 5. There's a whole bunch of 5s sitting here that represent a quarter of the data. So anytime you're seeing missing parts of a box plot, that means you have a bunch of repeated values. If you're drawing a box plot by hand, you'll see this when 2 or more of your 5-number summary values are the same value. And in that case, that part of the box plot will be missing. The other special case that you might see is a box plot with outliers drawn out explicitly. So we've got a nice example here. You might see a box plot that has the typical box and whiskers, but instead of a line here at the end to cap off the min, there's a couple dots at the bottom and a dot at the top. Those dots represent outliers. So sometimes you will encounter box plots with dots on the outer edge. Those are those extreme values. In cases where the graph has outliers, the minimum is replaced with the lower bound for outliers, Q1 minus 1.5 IQR, and the max is replaced with Q3 plus 1.5 times the IQR. So we're making it very clear, based on the rest of our data, where those kind of reasonable bounds are based on the middle 50% of our data. And then anything beyond those cutoff values are marked as dots. You don't have to do that, but if you're working with sets of data where it's really important you know where the outliers are, this makes it very clear. So if you see a box plot with dots in it, that's what it's indicating. It's indicating there are outliers in the data set. Okay, if you've got questions about box plots or use of technology, let me know. Otherwise, I will see you in our next video.